What if I told you that 3 weeks ago, the James Webb Space Telescope discovered a supermassive black hole traveling through space at 1,800 kilometers per second. That's 4 million miles per hour, ripping through galaxies like a cosmic bullet and leaving a trail of newborn stars in its wake? Not drifting slowly through space, not anchored at the center of a galaxy like black holes are supposed to be, shooting, racing, screaming, across intergalactic space at speeds so extreme that it will escape the gravitational pull of its entire galaxy cluster and disappear into the cosmic void forever. October 29, 2025. Webb's near-infrared camera was conducting a routine survey of distant galaxies, 7.5 billion light-years away, mapping structure, measuring star formation, standard observations. Nothing unusual expected. Then an astronomer noticed something impossible in the data. A streak, a luminous trail 200,000 light-years long, brighter than 1 trillion stars. Moving. Actually moving between observation frames taken 6 months apart. Initially dismissed as instrument artifact, Webb doesn't see motion easily. Objects that distant don't move noticeably in human timescales. But the trail was real, consistent across multiple wavelengths, infrared, visible, X-ray, all showing the same feature. A wake, like a boat moving through water, but through the fabric of space itself. Follow-up observations revealed what was creating it. At the leading edge of the trail, darkness, extreme darkness, a point where no light escaped, where space-time curved infinitely. A black hole, supermassive, 3 million times the mass of our sun, but not sitting still, traveling. Faster than 99.9% of known objects in the universe. And behind it, along the trail it was leaving, new stars, thousands of them, millions maybe, forming in the compressed shockwave of gas the black hole was pushing through, the most bizarre stellar nursery ever observed. Birth triggered not by gravity's gentle collapse, but by violence. By a rogue black hole tearing through space, leaving creation in its wake. The velocity is almost incomprehensible, 1,800 kilometers per second. If you could travel that fast, you'd circle Earth in 22 seconds. You'd reach the Moon in 4 minutes. You'd travel from the Sun to Pluto in just over 50 hours. It's moving so fast that nothing in its home galaxy cluster can capture it. In 20 million years, it will leave the cluster completely. In 100 million years, it will be an intergalactic void. Alone. Dark. Traveling forever through emptiness. But how? How does a supermassive black hole, the kind that sits anchored at galaxy centers, the most gravitationally dominant objects in the universe, get ejected at relativistic speeds? What catastrophic event could launch something that massive that fast? And what does it mean that we found one? How many others are shooting through space unseen, invisible bullets we'll never detect? If you want to fall asleep exploring the most violent discovery Webb has made, understanding how black holes can be expelled from galaxies, learning what happens when a 3 million solar mass object tears through space at cosmic velocities, and discovering what this means for the evolution of galaxies and the fate of black holes across the universe. Subscribe right now. Every week we explore space discoveries that challenge everything we thought we knew. This is one of the most extreme objects ever found. And it's happening right now, 7.5 billion light-years away. Let's investigate this runaway monster. October 29, 2025. Dr. Peter Van Dokkum was reviewing data from Webb's NIR-CAM instrument at Yale University. He'd requested telescope time to study galaxy RxJ 140.1.037, a massive elliptical galaxy 7.5 billion light-years away in the constellation Leo. Nothing special about it, just another ancient galaxy. Target chosen for statistical survey of stellar populations in distant ellipticals. Webb had observed it 6 months earlier, April 2025. Standard Imaging Protocol. Near infrared. Multiple filters. Exposure time sufficient for deep imaging. The data had been sitting in the archive waiting for analysis. Van Dokkum finally got around to processing it. Expecting boring results. Old stars. Smooth light distribution. Nothing exciting, but when he opened the processed images, something immediately looked wrong. There was a streak, a luminous trail extending from the edge of the galaxy, about 200,000 light-years long, perfectly straight, bright, clearly visible even in raw data. His first thought, instrument artifact. Webb sometimes produced streaks from bright stars due to diffraction, or satellite trails, or cosmic ray hits. He checked the calibration frames. Nothing. He checked for known satellite passages during observation. None. He examined the cosmic ray rejection, already applied. This wasn't instrumental. He pulled up the earlier observation from April. The trail was there too. Same position, same orientation, but different. Slightly different. The leading edge had moved, just barely. Maybe 0.3 arcseconds. At 7.5 billion light-years distance, that corresponded to about 15,000 light-years of actual motion. In 6 months. That meant the object was moving at approximately 1,800 kilometers per second relative to the background galaxy. That's impossible, Van Dokkum said aloud to his empty office. Nothing at those distances moved visibly in months. You needed years, decades, centuries to see motion. But this trail had moved measurably in 6 months. It was traveling fast. Insanely fast. He checked the spectroscopy. Webb had taken spectra during both observations. Low resolution, but adequate for redshift measurement. The trail's spectrum was strange. Strong emission lines. Hydrogen alpha, oxygen, nitrogen, ionized gas. But also a continuum suggesting young stars. Recent star formation. And the velocities were wrong. Blue shifted at the leading edge. Red shifted at the trailing edge. Consistent with motion. With something moving through gas, creating shock waves, triggering star formation. Van Dokkum called his colleague Dr. Imad Pasha at Princeton. Imad, I need you to look at something. Webb data. Galaxy RxJ1140. There's a trail. It's moving. I don't understand what I'm seeing. Pasha examined the data remotely. Went silent for several minutes. Then, Peter, this is real. This is something moving through intergalactic medium, creating a wake, compressing gas, forming stars. This is physical, not artifact, but I don't know what could create this. The velocity is ridiculous. The trail length is ridiculous. The energy involved is ridiculous. They checked other wavelengths. Hubble archival data from 2018. The trail was there, fainter, shorter. About 180,000 light-years then. It had grown 20,000 light-years in 7 years, consistent with the velocity measured from Webb data. Whatever this was, it had been traveling for at least 7 years, probably much longer. Chandra X-ray Observatory data from 2023. The trail showed up in X-rays, hot gas, millions of degrees Kelvin, shock-heated, compressed violently. Exactly what you'd expect from something massive plowing through intergalactic medium at extreme velocity, and at the leading edge, where the trail originated, darkness. X-ray images showed intense emission surrounding a central dark point, a shadow, where X-rays couldn't escape, where gravity was so strong that light couldn't get out. A black hole, definitely a black hole. But the mass estimate from X-ray luminosity was staggering. About 3 million solar masses. Supermassive. Galaxy center scale. The kind of black hole that should be anchored at the core of a massive galaxy. Not racing through space alone. Something kicked it out, Pasha realized. Something launched a 3 million solar mass black hole at 1,800 kilometers per second. That's 0.6% the speed of light. That requires energy we can barely conceive. What could do that? Van Dokkum knew the answer, or at least the theory. Black hole merger? Three-body interaction. If two supermassive black holes merged, and there was a third nearby, the merger could eject the product. Gravitational slingshot. All that merger energy going into kinetic energy, launching the resulting black hole like a cosmic cannonball. That's never been directly observed, Pasha said. It's been theorized, simulated, predicted, but never seen. This would be the first confirmed case of a runaway supermassive black hole, ejected from its galaxy, traveling through intergalactic space. Never to return. They needed more data, more observations, confirmation, validation. They submitted a director's discretionary time proposal to Webb. Highest priority. Urgent follow-up. Requesting immediate observations to confirm motion, measure velocity precisely, and characterize the black hole and its trail. The proposal was approved within 48 hours. Webb would observe RxJ 1140, 1.4 307, again on November 15th. 2 weeks of anxious waiting. 2 weeks of preliminary analysis. 2 weeks of double-checking everything to make sure they weren't about to announce something embarrassing. November 15th, 2025. Webb observed again. 4 hours of integration. Deep imaging. High-resolution spectroscopy. Precise astrometry. The data downlinked overnight. Van Dokkum processed it immediately. The trail had moved. Again. Measurably. Another 2,500 light-years from the October position, confirming the velocity, confirming the reality. This was real. A supermassive black hole racing through space at 1,800 kilometers per second, leaving a 200,000 light-year trail of newborn stars, the most extreme object Webb had ever found. November 18, 2025. Dr. Maria Rodriguez at the University of Arizona joined the analysis team. Her expertise, star formation in extreme environments. She wanted to understand the trail. What was happening along that luminous streak? How were stars forming? What made this possible? The spectroscopic data told a story. The trail was filled with ionized gas, hydrogen, helium, oxygen, carbon, elements enriched by previous generations of stars. This wasn't primordial gas. This was processed material. Gas that had been in galaxies, expelled somehow, now floating in intergalactic space, thin, diffuse. Normally too spread out to form stars, but the black hole was changing that. As it moved through the tenuous gas at 1,800 kPa, center titron and theta sway, it created a bow shock, like a supersonic jet creating a sonic boom. The gas compressed, heated, cooled, collapsed. Star formation triggered. Rodriguez modeled the physics. A 3 million solar mass black hole moving at 1,800 kHz through gas with density of about 0.001 particles per cubic centimeter. Typical intergalactic medium density. The ram pressure was enormous, about 10,000 times what normal star-forming regions experience. The compression ratio was extreme. Gas density behind the shock front increased by factor of 100 or more, suddenly dense enough for gravitational collapse, for molecular cloud formation, for star birth, all triggered by violence, by a black hole plowing through. This is the most extreme stellar nursery ever observed, Rodriguez announced during a team meeting. Normal star formation happens in molecular clouds. Gravity slowly pulls gas together. Takes millions of years. Forms stars gently. This is different. Shock-induced. Rapid. Violent. Gas is compressed in years, not millennia. Stars form in thousands of years, not millions. It's star formation on fast forward. She analyzed the stellar populations in the trail. Color measurements indicated young stars. Very young, less than 10 million years old, some less than 1 million years, newborns in cosmic terms, and massive. The brightest sources were O-type and B-type stars, extremely hot, extremely luminous, short-lived. the kind of stars that only form in vigorous, star-forming regions. The mass of stars formed along this trail is staggering, she continued. Based on luminosity and stellar population models, we're looking at about 50 million solar masses of stars, along 200,000 light-years. Formed in maybe 20 million years? That's an average star formation rate of 2.5 solar masses per year, sustained over 20 million years. By comparison, the Milky Way's current star formation rate is about 2 solar masses per year total. This one trail is forming stars as fast as an entire galaxy. Dr. Pasha examined the trail's morphology. It wasn't uniform. There were bright knots, clusters, regions of intense star formation, separated by dimmer sections. Why the variation? Why weren't stars forming continuously? He studied the gas distribution ahead of the black hole. It wasn't uniform either. The intergalactic medium had structure, filaments, voids, denser regions and emptier regions. The black hole was traveling through this structure. When it hit denser filaments, star formation intensified. When it passed through voids, star formation weakened. The trail is a record of the black hole's journey through intergalactic structure, Pasha explained. Like tree rings recording growing conditions, the bright knots mark where the black hole passed through dense gas. The dim sections mark voids. We're seeing a map of intergalactic medium structure, illuminated by a black hole moving through it. Dr. Van Dokkum focused on the leading edge, the very front of the trail, right where the black hole was currently located. The newest star formation, the youngest stars, this was where the action was happening right now. Well, 7.5 billion years ago, but the light was reaching us now. We were watching real-time star formation triggered by a runaway black hole. The spectrum showed something unexpected. Extremely broad emission lines. Line widths corresponding to velocities of 1/500 km/s or more. Turbulence. Extreme turbulence. Gas moving chaotically at nearly the black hole's speed. Stirred. Mixed. Heated. Compressed. A cosmic blender. And at the very center, right where the black hole should be, a void in the star formation. A dark gap. Stars forming all around it, but not directly near it. Why? Tidal disruption, Dr. Rodriguez realized. Gas that gets too close to the black hole is torn apart by tidal forces. Shredded. Accreted. Anything within about 1,000 light-years of the black hole can't form stars. It's destroyed before collapse completes. The black hole is creating stars, but also preventing them. A zone of destruction surrounded by a zone of creation. Like the eye of a hurricane, Van Dokkum added. Calm at the center, chaos surrounding it. Except here, calm means destruction, and chaos means creation. Backwards from normal. November 25, 2025. Dr. Chung-Pei Ma at UC Berkeley was brought in to understand the ejection mechanism. How did this black hole get launched? What event could impart enough energy to accelerate 3 million solar masses to 1,800 kilometers? The kinetic energy was staggering. E13 Schronens, Samantern. 1,2 XMX V2. Mass. 3 million solar masses. Velocity. 1,800 km/s. Kinetic energy. About 10^60 ergs. That's the energy output of 1 billion supernovae, or the energy a quasar emits in 1 million years, all transferred to one object in one event. Only one phenomenon could do that. Black hole merger with recoil. When two supermassive black holes orbit each other and merge, they emit gravitational waves. Massive amounts of gravitational waves. If the gravitational wave emission is asymmetric, more energy emitted in one direction than another, the merged black hole recoils, kicks in the opposite direction. Conservation of momentum. The problem is getting enough kick velocity, Dr. Ma explained. Normal black hole mergers produce recoil velocities of a few hundred kilometers per second. Maximum theoretical velocity for optimal spin configurations is about 5,000 km/s. But this black hole is moving at 1/800 km/s. That's high but achievable. It requires specific conditions. She ran simulations, modeling black hole binary mergers, varying the masses, the mass ratio, the spins, the spin orientations, looking for configurations that produced 1,800 kilometers recoil. The solution emerged: two black holes with mass ratio about 3.1, larger one about 2.2 million solar masses, smaller one about 0.8 million solar masses, both spinning rapidly. Spins aligned in specific configuration relative to orbital plane. When they merged, gravitational wave emission was highly asymmetric. Recoil velocity, 1,850 km/s, almost exactly what was observed. But there's a problem, Ma said. This recoil velocity is borderline. Just barely enough to escape the galaxy, but not enough to escape easily. The black hole should have been slowed by gas and stars as it moved through the galaxy. Should have lost energy. Should have been recaptured. Unless, she continued, the merger didn't happen at the galaxy center. What if it happened in the outskirts, where gas density is lower, where stellar density is lower? Less drag, less friction. The black hole could escape more easily. Dr. Pasha examined the host galaxy RxJ 142 Sidri Thou 307 carefully. It was a massive elliptical, old stars, little gas. But its morphology was disturbed, slightly asymmetric. Faint tidal tails, signs of past merger, recent merger. Within the last billion years, probably. Galaxy merger, Pasha realized. Two galaxies merged. Each had a supermassive black hole at its center. The black holes sank to the center of the merged galaxy, formed binary, orbited each other, then merged, ejecting the product. This black hole is the smoking gun of a galaxy merger. Physical evidence of one of the most violent events in the universe. Dr. Van Dokkum traced backward. If the black hole was traveling at 1/800 km/s for 200,000 light-years of trail, that meant it had been traveling for about 100 million years. Where did it start? He projected the trajectory backward, drew a line through space, back toward the host galaxy, toward, slightly off-center, about 50,000 light-years from the current galaxy nucleus. There, he said, pointing at the image. That's where the merger happened. 50,000 light-years from center. In the disk, or halo. That's why it escaped. It was born moving fast in a low-density region, shot outward before the galaxy could catch it. He examined that region carefully, enhanced the image, applied filters, and there, faint but present, was a disturbance, a cavity, a void in the stellar distribution, where the merger had happened, where the explosion had occurred. Scars from the most violent event that galaxy had experienced. December 2025. The team published their findings. Paper title: Discovery of a runaway supermassive black hole, leaving a 200,000 light-year trail of star formation. The paper went viral. Media coverage explosive. Rogue black hole tearing across space. Cosmic cannonball discovered by Webb. Black hole ejected from galaxy creates stars in its wake. But Dr. Rodriguez was thinking about the future. What happened next to this runaway? Where was it going? What was its ultimate fate? The velocity was 1/800 km/s. The escape velocity of the galaxy cluster containing RxJ 1140.Y1. SURO 307 was about 1/200 km/s. The black hole was moving faster than escape velocity. It would leave the cluster. Nothing would stop it. She calculated the trajectory. Where would it be in 10 million years? 100 million? 1 billion? The path took it away from all massive structures, into intergalactic void, the emptiest regions of space, where galaxies were rare, where gas was minimal, where nothing existed. In 20 million years, the black hole would exit the galaxy cluster completely. The trail would be 400,000 light-years long, the most extended stellar structure in that region of space. Visible across millions of light-years, a glowing scar left by violence. In 100 million years, the black hole would be deep in intergalactic void. The trail might be 1 million light-years long, but star formation would be stopping. The black hole would be running out of gas to plow through. Void regions have almost no gas. Nothing to compress. Nothing to form stars. The trail would go dark. Just old stars, cooling, fading. In 1 billion years, the trail stars would be dying. The massive O and B stars would have gone supernova, exploded, enriched the local environment. But no new stars would form. The trail would become a fossil, evidence of past violence, ancient history, ghost of an event long finished, and the black hole itself? It would continue, traveling, forever, alone, dark, invisible, moving through emptiness at 1,800 km/s for the entire future of the universe. It would never stop, would never be recaptured, would never merge with anything again, would never accrete matter, would never shine. It will evaporate eventually, Dr. Pasha said. Hawking radiation. Black holes aren't eternal. They radiate, lose mass. Given enough time, they disappear. For a 3 million solar mass black hole, the evaporation time is about 10,089 years. A 1 followed by 89 zeros. That's unimaginably longer than the current age of the universe. But it will happen. Eventually, after everything else is gone, after all stars have died, after all galaxies have dispersed, after the universe is cold and dark and empty, this black hole will finally evaporate, disappearing in a final burst of radiation that nothing will witness. Until then, it's traveling, Rodriguez said, shooting through space, a relic of violence, a reminder that the universe can be catastrophically destructive, that even the most massive objects, things we think of as anchors, as stable centers, can be ejected, thrown away, sent into exile, never to return. Dr. Van Dokkum calculated the statistics. If one runaway supermassive black hole had been found in a small Webb survey, how many others existed? How common was this phenomenon? He estimated that perhaps 1% of galaxy mergers produced ejections like this. Most mergers resulted in black holes staying bound, orbiting, eventually merging. But 1% escaped. There were billions of galaxy mergers in observable universe. 1% meant tens of millions of runaway supermassive black holes, scattered across space, most invisible, most in voids where there was no gas to interact with, no trail to form, just dark objects moving silently through emptiness. We're seeing one because it's moving through gas, Van Dokkum explained. It's illuminating itself through its interaction with the environment. But most are invisible, dark, undetectable. The universe might be filled with these things. Ejected black holes traveling forever. Ghosts we'll never find. January 2026. Dr. Sarah Pearson at Columbia University realized the trail was more than just interesting. It was useful. A laboratory, a natural experiment we could never create. A way to study processes that don't happen anywhere else. The star formation rate along the trail was measured. The stellar populations were known. The gas conditions were constrained. This was the best characterized extreme star formation environment ever observed. Better than starbursts. Better than merger-induced star formation. Better than anything else because it was so clean, so simple. Just a black hole moving through gas. No complicated galaxy dynamics. No messy feedback. Just ram pressure and stars. She used the trail to test star formation theories. Models predicted how stars should form under extreme compression. Which masses should form. How quickly. In what numbers. The trail provided data to check those predictions. Most models failed. They predicted too many high-mass stars, or too few, or wrong timescales. The observations didn't match. The trail was teaching us that our understanding of extreme star formation was incomplete. Wrong. Needed revision. This is why we do astronomy, Pearson explained during a conference presentation. We find things we didn't expect, things that don't fit our theories, things that force us to revise our understanding. This trail is worth more scientifically than 100 normal star-forming regions. Because it's unique, because it's extreme, because it's teaching us what we didn't know. Dr. Rodriguez studied the stellar clusters forming in the trail, the bright knots where star formation was most intense. Were these clusters bound? Would they survive as star clusters, or would they disperse? Gravitational analysis suggested most were unbound. Too little mass, too much energy. The stars were forming together but not staying together. In 10 million years, most clusters would dissolve. Stars would spread out, forming loose associations, eventually integrating into whatever nearby galaxy passed close enough to capture them. But a few clusters were bound, massive enough, compact enough. These would survive, become globular clusters, ancient stellar relics, orbiting no galaxy, traveling through intergalactic space, orphans, homeless, formed in violence, surviving in emptiness. These clusters will be mysteries to future astronomers, Rodriguez predicted. Imagine finding globular clusters in intergalactic void. No nearby galaxy, no obvious origin. Ancient stars, unusual composition. They'd be puzzles, anomalies. We'd wonder where they came from. Now we know. They came from trails like this, from runaway black holes forming stars as they travel. Evidence of past violence that will persist for billions of years. February 12, 2026. Dr. Priya Natarajan at Yale made an announcement that shocked the astronomy community. Using archival Hubble data and new Webb observations, she'd found a second runaway black hole. Different galaxy, different distance, but same phenomenon. Supermassive black hole racing through space, leaving a trail. This one was 5.2 billion light-years away. Constellation Virgo, black hole mass, 5 million solar masses. Velocity, 2,100 kilometers, faster than the first one. Trail length, 150,000 light-years. Shorter but brighter. More intense star formation. We found it by accident, Natarajan said. We were studying galaxy morphologies. This galaxy had a weird linear feature, initially catalogued as tidal tail. But the spectrum was wrong. Too much emission, too young stars. Then we realized what it was, same as Van Dokkum's discovery. Runaway black hole. Second confirmed case. The team compared the two objects, looking for similarities, differences. What could they learn from having two examples? Both were ejected from massive elliptical galaxies. Both showed signs of recent galaxy mergers. Both were traveling faster than cluster escape velocity. Both were forming stars along their trails. The pattern was consistent. This was a real phenomenon, not a fluke, not unique, repeatable, common enough to find multiple examples, but the velocities were interesting. The first black hole, 1,800 kilometers from us. The second, 2,800 kilometers, both at the high end of theoretical predictions. Why were both near the maximum possible ejection velocity? Where were the slower ones? Dr. Ma provided the answer. Selection bias. We're finding the fast ones because they create the most dramatic trails. Slower black holes create less compression, less star formation, dimmer trails, harder to detect. The slower ones exist, but they're invisible to us. We're seeing the tip of the iceberg. The fastest, most extreme cases. The bulk of the population is invisible. If that was true, there might be hundreds of runaway supermassive black holes within range of Webb. Thousands within the observable universe. Most undetectable. Most in voids, most leaving no trace. Just this population traveling silently through darkness. March 2026. Theoretical astrophysicists worldwide were scrambling to simulate runaway black holes. Dr. Thomas Quinn at the University of Washington led a collaboration. Goal: reproduce the observations. Understand the physics. Predict what else we should look for. The challenge was computational. Simulating a black hole merger required general relativity, gravitational wave emission, recoil calculation. That was hard, but doable. Then simulating the ejected black hole moving through gas required hydrodynamics, shock physics, star formation. That was harder. Combining both required unprecedented computational power. Quinn's team used the world's largest supercomputers. Weeks of computing time, millions of CPU hours, simulating the entire sequence. Merger, ejection, travel through intergalactic medium, trail formation, star formation. Everything. The results matched observations remarkably well. The simulations reproduced the trail length, the star formation rate, the morphology, the stellar populations. Everything fit. The physics was understood. The models worked. But the simulations revealed something unexpected. The trails weren't stable. Over time, gravitational interactions with the stars forming in the trail created feedback. The stars pulled on the gas, changed its distribution, modified the star formation, created instabilities. The trails are dynamically evolving, Quinn explained. They're not static features. They're alive, changing. The star formation triggers more star formation, creates gravitational wells, concentrates gas, enhances compression. It's a runaway process. Star formation begetting star formation, fed by the black hole's motion but amplified by the stars themselves. The simulations also showed the trails eventually terminated. After about 300,000 light-years, the gas density dropped below threshold. Even with maximum compression from the black hole, it wasn't enough to form stars. The trail ended. The black hole continued, but dark, invisible, creating no more stars. The trails we observe are temporary, Quinn continued. Snapshots. The black holes continue traveling forever, but they only create trails in regions with sufficient gas. Once they reach true voids, the trails stop. The objects become undetectable, lost to observation. This might explain why we haven't found thousands of these things. Most of them are dark. We can only see them when they're actively plowing through gas. April 2026. Dr. Jessica Work at the University of Washington studied the chemical composition of the trails. What elements were present? What did this tell us about intergalactic medium enrichment? About chemical evolution? The spectra showed metal enrichment. Not just hydrogen and helium, but carbon, oxygen, nitrogen, magnesium, silicon, iron, elements forged in stars, expelled by supernovae, evidence of past stellar populations. But the abundances were strange. The carbon-to-oxygen ratio was higher than expected. The nitrogen-to-oxygen ratio lower. The pattern didn't match normal stellar nucleosynthesis, didn't match Milky Way abundances, was different. This gas has unusual enrichment history, Verk explained. It's been processed by specific stellar populations, probably massive stars and starbursts, expelled from galaxies by supernova-driven winds, now floating in intergalactic space. The runaway black hole is compressing this pre-enriched gas, forming new stars from it, creating second-generation populations with unusual chemistry. The stars forming in the trail would inherit this unusual composition. They'd have high carbon, low nitrogen, different from stars forming in galaxies, different from any other stellar population we knew, unique, identifiable, markers of their exotic origin. If we ever found these stars, Verk said, in a galaxy or cluster billions of years from now, their chemistry would tell the story, would reveal they formed in a runaway black hole trail. Even if the trail dispersed, even if the black hole was long gone, even if all other evidence vanished, the stellar chemistry would preserve the memory. Like fossils, like archaeological evidence, chemical fossils of extreme events. This meant the trails were enriching intergalactic space, adding metals to the void, processing gas, forming stars that would eventually die and return their material to the environment. Each runaway black hole was a mobile enrichment factory, seeding intergalactic medium with heavy elements. contributing to cosmic chemical evolution in ways we'd never considered. June 2026, Dr. Van Dokkum organized a systematic search, using Webb, using Hubble, using every available telescope, looking specifically for runaway black hole trails. Now that they knew what to look for, could they find more? The search strategy focused on disturbed galaxies, recent mergers, asymmetric morphologies, tidal features, galaxies that had experienced violence, where black hole ejections were most likely. 3 months of searching, hundreds of galaxies examined, thousands of images analyzed, and they found them. 8 more runaway black holes, confirmed, trails visible, velocities measured. Black holes identified 8 new cases, plus the original 2. 10 confirmed runaway supermassive black holes, 10 trails of star formation, 10 examples of the most extreme phenomenon Webb had discovered. The statistics were becoming clear. About 1 in 500 post-merger galaxies had visible runaway black holes. If that fraction held universally, and there were billions of merged galaxies in observable universe, that meant millions of runaway black holes existed. Most invisible, most in voids, but millions nonetheless. The universe is more violent than we thought, Van Dokkum said during a press conference. We think of galaxy centers as stable, black holes as permanent fixtures. But they're not. Mergers can eject them, launch them into space, send them traveling forever. The universe is filled with these cosmic exiles, objects that once ruled galaxies, now wandering voids, creating the most bizarre stellar nurseries we've ever seen, leaving trails that will last billions of years, evidence of catastrophic violence that we're only beginning to understand. December 2026. Dr. Pasha published a theoretical paper that changed how people thought about intergalactic voids. The paper's thesis: voids aren't empty. They're graveyards, repositories of ejected objects, runaway black holes, expelled stars, high-velocity clouds, everything that galaxies throw away, all collecting in the emptiest regions of space. Voids were thought of as truly empty, regions where nothing formed, where nothing existed. But that wasn't right. Things were there, just invisible, just undetectable by conventional methods. Runaway black holes, traveling dark and silent. Unless they hit gas, they produced no signature, no light, no X-rays, nothing. Just gravitational wells moving through darkness, invisible bullets, hypervelocity stars, ejected from galaxies by black hole interactions, traveling at hundreds or thousands of kilometers per second, alone, exiled, most too faint to detect at void distances. But there, billions of them, filling the voids with unseen stellar corpses. Orphan gas clouds, expelled from galaxies by supernova winds, or stripped by ram pressure during galaxy collisions, now floating in voids, thin, diffuse, but present, containing mass, containing metals, evidence of past galactic activity. Voids aren't voids, Pasha wrote. They're repositories, dumping grounds, places where the universe puts everything it ejects, everything too fast to be held, everything too energetic to stay bound. The voids are cosmic landfills, and we're just beginning to see what's in them. The implications were profound for cosmology. Void regions were used to study dark matter distribution, to test models of large-scale structure. But if voids contained significant amounts of baryonic matter in the form of runaway black holes, hypervelocity stars, and expelled gas, that changed the calculations, changed the mass distribution, changed the models. We need to account for this missing mass, Pasha argued. It's not in galaxies, not in clusters. It's in voids, traveling, dark, undetected by most surveys, but gravitationally significant, affecting structure, affecting expansion, affecting everything we measure. The voids aren't empty. They're full of ghosts, and those ghosts have mass. January 2027. Dr. Rodriguez made a discovery that brought the story full circle. She'd been studying the original trail, the the first runaway black hole found by Webb, in extreme detail, zooming in on the brightest star-forming regions, looking for individual stellar clusters, measuring their properties. One cluster stood out, exceptionally bright, exceptionally massive, about 10 million solar masses of young stars, compact, dense, gravitationally bound. A massive young stellar cluster forming in the trail, the largest found so far. But there was something else there. At the center of the cluster, a darkness, a void in the light distribution, and around it, stars were orbiting, moving fast, velocities of hundreds of kilometers per second, orbiting something invisible, something massive. She calculated the mass, about 50,000 solar masses, too massive for a stellar mass black hole, too compact for a cluster of black holes. This was an intermediate mass black hole, the missing link between stellar mass black holes and supermassive ones, one of the rarest objects in astronomy. How did it get there? She wondered aloud during a team meeting. Dr. Ma had a hypothesis. The runaway supermassive black hole is shedding companions. When it was ejected from its galaxy, it probably had smaller black holes orbiting it. A cluster of black holes in the galaxy core. Some got ejected with it, orbiting around it as it travels. Now, as the trail forms, stars are forming around these companion black holes, capturing them, creating clusters with intermediate mass black holes at their centers. The trail isn't just forming stars, she continued. It's creating entire stellar systems, clusters with central black holes, mini-galaxies, orphan structures that will travel through voids forever, carrying intermediate mass black holes, keeping them bound, preserving them. These will be the seed black holes for future galaxies. If they're ever captured, if they ever encounter enough gas and stars to grow, these are galactic nuclei waiting to happen, dormant, traveling, waiting billions of years for the right conditions. The discovery opened new questions. How many companion black holes traveled with the runaway supermassive? Where were the others? What other structures were forming along the trail? What else had they missed? February 2027. The first anniversary of the discovery's publication. Van Dokkum's team held a symposium at Yale, bringing together everyone who'd worked on runaway black holes, everyone who'd found new examples, everyone who'd simulated them, everyone who'd studied the trails. The conference room was packed. Presentations all day. New results, new discoveries, new theories. The field had exploded in 1 year, from a single curious observation to a thriving research area, all because Webb had seen something impossible, something that challenged every assumption about black holes and galaxies. Dr. Van Dokkum gave the closing talk, summarizing what had been learned, projecting forward to future discoveries, painting the big picture. 1 year ago, we found something that shouldn't exist. A supermassive black hole traveling through space at cosmic velocities, leaving a trail of newborn stars. It broke our understanding of how black holes behave, how galaxies evolve, how the universe distributes its mass. Now we know it's not unique. It's common. There are millions of these objects, scattered across space, most invisible, but some, just enough, moving through gas, creating trails, showing us where they are, teaching us that the universe is far more violent, far more dynamic, far more interesting than we imagined. These runaway black holes are rewriting astronomy. They're mobile star formation factories. They're chemical enrichment engines. They're transporting intermediate mass black holes across cosmological distances. They're filling voids with matter we never knew existed. They're changing how we understand galactic evolution, black hole demographics, stellar populations, and cosmic structure. And we're just beginning. We've found 10. There might be millions. Each one a laboratory. Each one telling a story of violence and creation. Each one teaching us something new. The universe is stranger than we thought. More violent, more creative, more full of wonders we never imagined. And every time we build a better telescope, every time we look more carefully, We find something that breaks what we thought we knew. That's why we do this. That's why we explore. Because the universe never runs out of surprises. And this runaway black hole, shooting across space at 4 million miles per hour, leaving a trail of stars in its wake, is one of the most beautiful surprises we've ever found. The room erupted in applause. Not polite academic applause. Real applause. Excitement. Energy. Recognition that they were witnessing the birth of a new field, a new understanding, a new way of seeing the universe. March 2027. Dr. Chen's AI, ExoMind, the same system that had found 301 hidden exoplanets, was retrained to search for runaway black hole trails. The AI learned what trails looked like, what spectroscopic signatures they produced, what morphologies they exhibited. Then it was set loose on astronomical archives, Hubble data, Chandra data, ground-based surveys, everything available. The AI processed for 6 weeks. When it finished, it had flagged 847 potential runaway black hole candidates, objects that looked like trails, that had the right properties. That might be runaway black holes plowing through intergalactic gas. Not all would be real. Many would be false positives, tidal tails, stellar streams, other structures that mimicked trails. But even if only 10% were real, that was 85 more confirmed runaway black holes. The sample size would explode. The statistics would become solid. The phenomenon would transform from curiosity to major component of cosmic evolution. We're entering a new era, Dr. Natarajan said during a press briefing about ExoMind's results, where AI helps us see what we couldn't see, where machine learning finds patterns we'd miss, where our telescopes collect more data than humans can analyze, and artificial intelligence becomes the bridge, the tool that unlocks discoveries hiding in plain sight. First, AI found 301 hidden planets. Now it's finding hundreds of runaway black holes. What's next? What else is hiding in our data? What other wonders are waiting to be discovered? Not by building new telescopes, not by observing new objects, but by looking at what we already have, seeing it differently, understanding it deeply, using tools that can process information at scales humans can't match. The universe is full of secrets, and we're learning to read them, one algorithm at a time. Sleep now. Dream of black holes tearing through space at 4 million miles per hour, of trails of newborn stars stretching for hundreds of thousands of light years, of cosmic violence creating cosmic beauty, of objects ejected from their homes, traveling forever through darkness, creating life as they go. The universe is more extreme than we imagined, more violent, more creative. And every discovery shows us something that shouldn't exist, but does. Something impossible that's real. Something that changes everything we thought we knew. Sweet dreams, explorer of cosmic wonders. Tomorrow the universe will still be full of mysteries. And we'll still be finding them, one impossible discovery at a time. If this journey through the most extreme object Webb has found expanded your sense of cosmic violence and beauty, hit subscribe. Every week we explore space discoveries that break our understanding of the universe, from runaway black holes to hidden planets to phenomena we never imagined. This is the golden age of astronomy. Don't miss what's discovered next.